Hello scientific people, how are you today? Today we are going to discuss about one of the most important topic in nuclear physics. What is strong nuclear force and what holds all the protons together in a nucleus? So you can consider an atom to be a cricket stadium, and in the cricket stadium at the center there is a small pitch, right? And let's draw it. Suppose this is a cricket stadium and you are watching the cricket stadium from the top. Say for example you are sitting in an aeroplane and you are seeing the cricket stadium. At the center there is a pitch and you put a ball, cricket ball, at the center of the pitch. Then the entire cricket stadium is actually an atom, whereas this cricket ball is a nucleus. So you can imagine that how big is an atom compared to that of a nucleus, or vice versa. So we know that inside the nucleus we have protons and neutrons as shown over here, and all the protons, they are positively charged. So between two positive charges there should be a force of repulsion given by Coulomb's law. So in that way these brown colored dots are neutrons, whereas all other are protons. So what should happen is all these protons must repel one another and the nucleus must go off. I mean, it should break, because these protons would actually try to go out of the nucleus, making the nucleus very unstable. So these protons should actually leave the nucleus, which is not happening in any of the nucleus. That means there has to be some force which is holding all these protons together. So that force is called strong nuclear force, and we'll be talking about the strong nuclear force in quite depth. So first of all guys, strong nuclear force is attractive as well as repulsive both, and it actually depends upon the distance. So first property, it is distance dependent. If between two protons or two neutrons or a proton and neutron, like this, suppose this is a proton and this is a proton. Now between these two protons, the most stable distance at which they want to stay, that is 0.8 for me. We'll talk about this distance, why it is. So at this distance, these two protons, they would like to stay together. If the distance increases beyond this, then there would be net attraction and these two protons would come nearby each other. So what would happen is, if you try to increase the distance between them like this, suppose this is 1 for me. For me means 10 raised to minus 15 meters. Then you have increased the distance more than 0.8. So they would start attracting and they would again come to this particular distance. Okay, now what would happen if you decrease the distance below 0.8 for me? Suppose now the distance is 0.6 for me. Then this force will become repulsive and they will try to push the nucleons back at its own place. So the most stable distance at which any two nucleons, protons or neutrons, if they are at 0.8 distance, more than that this force will become attractive, less than that this force will become repulsive. So it is distance dependent force. It does not depend upon whether this is proton or neutron. Both may be protons, both may be neutrons. A proton or neutron, that means it is charge independent force also. So the most stable distance between them is 0.8. So it is actually attractive when the distance becomes more than 0.8 for me, and it becomes repulsive if the distance becomes less than 0.8 for me. Now let's understand why most stable distance between any two nucleons in the nuclei is 0.8 for me. So we would have a look at this particular graph. This is potential energy which is a function of distance versus the distance graph. This distance is measured from the center of the nuclei. So we can see that the minimum potential energy, this is U minimum, is corresponding to 0.8 Fermi distance. So least potential energy means most stable state. So that's why if I leave this pen, it is at a high potential because it is at a very large distance away from the ground. If I leave it, it is going to fall towards the ground, meaning it is going to lower its potential energy. So in the same way, this is the distance corresponding to minimum potential energy, so most stable distance. So all the nucleons will try to have this distance because at this distance they will have minimum potential energy, right guys? Okay, so if you increase the distance more than that, potential energy, you can see that if you increase distance more than 0.8, potential energy increases. So they would like to again decrease their potential energy and come back. So they will try to attract one another and they will try to decrease the distance. In the same way, if the distance between two nucleons decreases below 0.8 Fermi, again the potential energy increases. So it is becoming more unstable. So it would like to again decrease the potential energy by increasing the distance. So that means the force should be repulsive. Next thing, it is a charge independent force. Meaning the force between two neutrons or two protons or a proton or neutron. 0 is the charge of the neutron, is same at a fixed distance. Suppose if between two neutrons, two protons and proton neutron, if the distance is suppose 0.8 Fermi, then the force over here and force over here are same, right? Actually considering very microscopically, then the force between two protons would be slightly less than these two. The force between this and this would be equal, and the force between these two would be slightly lesser than these two because there is also Coulombian repulsion between them, whereas here and here there is no Coulombian repulsion, right? Okay, so in general we can say that the amount of force between these two and these two at a same distance 0.8 Fermi is same, right? So it is charge independent force. So that's why in a nucleus, if we talk about whether a proton or neutron, one and the same thing, that's why we have given a common name as nucleon. Third thing, it is a spin dependent force. In spin dependent force, that means suppose if we have two protons, pair of two protons, this is a proton, this is a proton, proton and proton at a same distance r, but the spin of these two protons are parallel and the spin of these two are anti-parallel. So the force over here is larger than the force over here. So when the spins are actually parallel, the effect of force is quite larger, right? Okay, next property, and very important property, it's a short range force. And its limit is actually up to 3 Fermi, 2.5 to 3 Fermi. So if you say that these are two protons which are at a distance of, say for example 5 Fermi, then you can't expect strong nuclear force between these two. Then there would be definitely a Coulombian repulsion force between them. So short range means its range is very small, approximately 2.5 to 3 Fermi, guys. Okay, so we have listed almost all the points, and we should also not forget about the equation of the potential energy as well. And the last one is, there are two more properties. One is the saturation property as well as the conservative nature. So we are going to talk about that in depth. So the potential energy equation for this, for any two nucleon pair in a nuclei, is given by, is a function of actually the distance, that is minus g square e raised to minus r by r upon r, where this g square is called strength parameter and this r is again a constant, and this r is the distance measured from the center of the nuclei, right? Okay, and now talking about the conservative nature as well, you might be wondering that you might have studied in many places that this is actually. So the fifth property of the strong nuclear force is it is conservative in nature. All the forces which are naturally there, all the fundamental forces which are naturally existing, they are all conservative in nature. And what happens is that in a nucleus, suppose in a proton there are 3 quarks. So this is a proton, so it is made up of U and D. So sometimes we do have a confusion that this is up quark. So in a given proton, 2 up quarks are in a same quantum state. So that's why as per the Pauli's exclusion principle, this is not explainable. That's why sometimes people think that this strong nuclear force is actually a non-conservative force, but it is not the same. All the 3 quarks, they are actually colored in nature, and we may talk about this particular concept in depth sometime later. And suppose this up quark is blue, this is green, and this is red, and the sum of all these 3 colors, we are assigning a color. Color is not a normal color that we talk about in a daily life, but color is actually a quantum state. So these 3 are being assigned a different quantum state by giving different colors, but when they add up, their color turns out to be neutral or 0. So on the basis of that, we can say that it is conservative in nature, and all the forces which are there in the nature are conservative. So any forces which are conservative, they can be related with potential energy by this particular expression, right? Okay, so this is the potential energy versus the distance graph. Distance is measured from the center of the nucleus in Fermi, and this is the point. Suppose this point I am giving name as B, this point is A, and this point is C. This point B is corresponding to minimum potential energy. Now what am I going to do is I am going to draw 3 tangents at these given distances, and corresponding to A, the distance is R1, corresponding to C, the distance is R2. R2 is larger than 0.8, R1 is less than 0.8. So suppose 2 nucleons, they are at a distance of 0.8 for me. So what's going to happen is at this point, the slope of this graph is du by dr, because change in y-axis upon change in x-axis. So the slope itself will give me the force, negative of the force. So force at B is equal to negative times slope, but the slope of this tangent is 0. So my answer is 0. So that means the net force on any 2 nucleons at this distance would be 0. So that's why all the nucleons inside the nuclei at this distance stay stable. No repulsion, no attraction, right? Okay. If we talk about force at A, then at point A the angle is obtuse, so the value of slope is going to be negative. So negative of negative slope turns out to be positive force, and positive force means repulsion. It's because suppose you have 2 charges, F is equal to K Q1 Q2 upon R square. If Q1 and Q2 both are positive, then there is definitely repulsion, and force is also positive. So positive forces means repulsion. At C, the force would be negative of the slope, but the slope is positive because the angle with x-axis is positive. So my answer is going to be negative, and negative means attraction. So we can say that if the distance between 2 nucleons, if it decreases by 0.8, then they would repel, and if it increases by 0.8, it would attract. But the range of the nuclear force cannot be beyond 2.5 to maximum 3 for me. So this graph would actually end up somewhere over there, and you cannot expect the force to be acting between 2 nucleons more than 2.5 to 3 for me. Now, the real explanation behind the strong nuclear force was given by Sir H. Yukawa, and he was a Japanese physicist, and he received Nobel Prize in 1949 for explaining how the strong forces act between two nucleons. So let's understand that. He gave such kind of example, like suppose you have two protons UUD and another proton UUD. Now between these two protons there is a continuous exchange of particle. These particles are called mesons, which are made up of quark and antiquark pair. So these mesons are being continuously exchanged between two protons or two neutrons or a proton neutron in a given nuclear range force. So due to these exchange particles, the nucleons are interacting and they exert strong nuclear force on each other. So finally, let's discuss about the saturation property of the nuclear forces. So here in a picture we have the nucleons. So this is a one nucleus, this is another nucleus, this is third, fourth, fifth and so on. So in this nucleus, one nucleon is surrounded by only another nucleon, and here one nucleon is surrounded by three nucleons, here one nucleon is surrounded by five nucleons, and here a nucleon is surrounded by six nucleon and so on. Here I have not increased the number for a specific reason. So these are all different nuclei, and we may consider proton or neutron because it is not going to affect our discussion, because strong nuclear forces does not care whether it is a proton or neutron, because they are all short range forces, attractive and repulsive, same for protons and neutrons. So suppose this is a nucleon, and this nucleon I want to pull it off from the nuclei. So this is case, suppose this is nuclei A, this is A, B, C, D, E and F. All are different nuclei, and if I want to pull out this green colored nucleon from the nucleus, so where it would be very difficult for me to pull out the nucleon. So let's understand this. So if I want to pull out this nucleon, and suppose this is within a nuclear force range, so if I actually pull this outside, then this nucleon would be attracting this nucleon towards itself. So if I want to pull it out, the distance between them increases, so there would be an increase in the attractive force, and this would again try to pull it backwards. So it would be difficult for me to pull this nucleon outside. Now if I want to pull this nucleon, there are three who are going to attract this particular nucleon, because if I pull it outwards, then all three are going to pull them inwards, so it would be quite more difficult for me compared to this situation. So I need to provide a larger amount of force in order to pull this outside. So over here, I think that you might have guessed it right. Here if I want to pull this outside, then if I want to pull this outside, then the distance between these nucleons with this will increase even more than 0.8 for me, and they all are going to attract. So 1, 2, 3, 4, 5, 6, actually 6 pulling in the backward direction, so it would be more harder for me to pull out this nucleon. So if I say that this is force F1, this is force F2 and force F3 is required in order to pull the nucleon outside, then the F3 out of these three would be the highest. In the same way, if I still increase the number like 7, 8, 9, 10 around it, maximum number of nucleons surrounding a particular nucleon is 12. That means you can consider, I won't be able to draw all the 12 because that would be a three-dimensional structure. So if this one, suppose 6 in the upper hemisphere, 6 in the bottom hemispheres, so that means there are 12 nucleons holding a particular nucleon at the center, 6 up and 6 down forming a sphere, and the 13th one or the green one at the middle. So what do you have? you have 12 nucleons surrounding the 13th green nucleon at the center. 6 nucleons on the upper half hemisphere, 6 nucleons in the bottom hemisphere. Maximum number of nucleons surrounding a particular nucleon is 12, because now you won't be able to adjust any more now. So suppose this is one nucleon, 1, now here 3, here 6. In that way, there are 12 nucleons surrounding a particular nucleons maximum to form a sphere. Now if I want to pull this green color nucleon outside the sphere, 12 nucleons are exerting attractive force. So that means I need to provide a huge amount of force, that is F4, and this F force would be the largest among all of these forces. Now suppose you might be thinking, what would happen if I place one more nucleon around it? So this is the green color nucleon at the center, 6 up and 6 down, so already there are 12 nucleons surrounding it. Now suppose the 13th nucleon, I am placing it over here like this. Now this 13th nucleon which I am placing is quite far away from the green nucleon. So this turns out that this nucleon is out of range of nuclear force, strong nuclear force, with respect to this one. So that means if I want to pull this green color nucleon outside, I need to provide force F5, but F5 would be equal to F4. It is because this nucleon is not going to affect this particular nucleon at the middle, because this is out of range now. So if in this way if I keep on putting the nucleons outside, these all nucleons are now out of range of this green color nucleon. So I need not to apply more amount of force over here. So suppose if the force over here is F6 in order to pull this outside, then this F6 would again be equal to F4 or F5, because these nucleons are out of range and they are not going to affect this, right? So what happens in the beginning is, as the number of nucleons increases, the force required to pull a particular nucleon outside increases, but then after it remains constant. So here we can sum up our discussion like this: F6 is equal to F5 is equal to F4, but that is greater than F3, that is greater than F2, and that is greater than F1. So that means the strong nuclear force increased and then became maximum, and that maximum remained as it is. So the nuclear forces, they increase and they saturate. That means they become constant afterwards. So hopefully guys you like my explanation, and don't forget to subscribe my channel. If you have any doubts, do comment in the comment section. Thank you for watching the video.